Hello all, welcome to my channel. So in the last lecture I did formation of p-n junction under semiconductor. So in this case we learned how depletion layer is formed and what is the function of it. Now after this we would be learning about biasing. So if you want the lecture for formation of p-n junction, you can check the description box. In this lecture, I would be considering the biasing. So first of all, you guys should know what biasing is. Biasing basically means like to provide potential, outside potential or the external potential. So in this, we would be connecting the PN junction with battery. So in this case, as you can see, I have already made a diagram for PN junction. So this is the PN junction formation, the simpler one, the above one. So in that you can see that we have a depletion layer. So in this case, when we do forward biasing, we are connecting P junction to the positive pole of the battery. So first of all, we need to draw the P junction with the battery with a positive pole. So it will be connected to a positive one. So let us draw here a positive potential, and a negative one is connected to the negative pole of the battery. So the P is connected to positive and the N is connected to negative pole. So this is what forward bias is. So when you connect P to positive pole and N junction with a negative pole, it is known as forward bias. Like now we need to know why we do this and what is the outcome of the same. Now in this case we are providing the potential to the PN junction here. Now what happens is, as you know that the p-type semiconductor has more number of holes as compared to the electrons as shown in the figure as well. And in n-type semiconductors, they mostly have electrons in it and less number of holes are present here. Now what happens when we provide an external field? As you know that we have a depletion layer here in between p-n junction. Now why it is formed, it is well discussed in the last lecture. So in this case, while we are providing the potential difference, what happens is, as you can see, we have a positive holes in the P section. So they are actually repelled by the positive pole. As you can see that it is connected here with a positive pole, so they are repelled by the positive pole of the battery, these positive holes. That means they will go to this direction. Now, the negative electrons in the n-type will be repelled by the electrons and holes across the junction, therefore opposed by fictitious battery here. As you know, we have a fictitious battery here in the middle because we have positive and negative charges in between the depletion layer. So we have a fictitious battery here. So now what happens is, in this case, this is the normal PN junction without any external battery. But when as soon as we provide an external battery, they form a low resistance path. As you can see, the junction, the depletion layer has been decreased very well. So if the depletion layer has been decreased, that means they will provide current to flow through this circuit. Hence, it is known as low resistance path. When we provide, when we put P side with the positive pole and N side with the negative pole, then they provide us with a low resistance path. That means the depletion layer has been depleted more. That means it has been reduced to many times. So whenever the depletion layer reduced, it will be due to the forward biasing. We need to do the forward biasing and hence it is eliminated altogether if we provide more potential to it. Now let us see the graph for same. As you can see, it is a VI graph. So I will take it as IF, that is on Y axis, and VF on X axis. So this basically means that we are increasing the potential as we go towards VF. So In this case, we need to provide the PN diode with some potential so that they can cross this barrier. As you can see, there is a sudden increase in the current. Why? Because as soon as they cross this barrier voltage, they will start diffusing into each other very fast. So if you take silicon, it will be of 0.7 volt. That means you need, as soon as you give the PN diode with 0.7 volt, the current will start increasing suddenly. So if you break this path, then the current will increase suddenly. So this is also known as barrier voltage. Until they cross this path, there won't be any sudden increase. So therefore, it is known as a low resistance path whenever we provide a forward bias to a PN junction. So it is silicon is 0.7 volt and the germanium one is 0.3 volt. So in this case, you need to provide germanium with 0.3 volt and the silicon with 0.7 volt. So as soon as they pass through this potential difference, the current will start flowing very quickly. So this is how the forward bias of PN junction works. Now in the second case, reverse bias of PN junction. So in this case, we have a high resistance path. Why high resistance path? Because in the P type you can see the holes will be attracted to the negative terminal. In the N type, electrons will be towards the positive terminal. And whenever we connect a battery, whenever we connect a battery of negative terminal to the P type and the positive terminal to the N type, they form reverse biasing. So remember this, and in this case the potential barrier is increased in depth, like you can see in the figure as well. Therefore, I mark this as a high resistance path because through this path no electrons and holes could flow through. A very small number of holes and electrons are left here in the vicinity of junction. So practically here no current take place in this path. If there would be any current, it will be due to the minority charges. Like in the minority charges, we have negative, so they will try to come here. The positive will try to come here, forming electron hole pair and forming a very little current here. So remember, for the forward bias, we have current due to the majority charge carriers. In the reverse bias, we have current due to the minority charge carriers because they only form the current here in the middle. So if the reverse bias is made very high, let us suppose that we made the reverse bias very high, all the covalent bonds here near the junction break and a number of electron hole pairs are liberated and the reverse current increases abruptly like is shown in the figure. So this is the IR and VR graph. IR is on the y-axis and VR is on the x-axis. So as soon as we increase the current or the voltage, there would be a sharp change in the voltage of the reverse bias of PN junction. So maximum reverse potential difference which a diode can tolerate without breakdown is known as the breakdown voltage. So this is the breakdown point for this PN junction. So what we need to know is that we have forward biasing and we have reverse biasing. In forward biasing, you have to attach p-type to the positive pole and n-type to a negative pole. And in the reverse bias, remember, you have to attach p to the negative part and n to the positive potential. So in this case, in the forward bias, the potential barrier is decreased and in the reverse bias, the potential barrier is increased therefore very less current flow through it. But in the case of forward biasing, there is a lot of current which we can generate. And remember, in the forward bias, the current is due to the majority charges, and in the reverse bias, the current is due to the minority charges, as you can see in this diagram, because the negative ones try to come here, and the positive ones try to come here, forming electron hole pair. If they will form electron hole pair, they will generate obviously electric current. So that's all for today's section. We'll continue with the rectifiers in the next class. Thank you for